right, we're at the top of the hour. Thank you everybody for joining us. And we'll get started with the talk. But hi, my name is Jenny and I'm from Edge Impulse. And today's tinyML talk is Smart Motion Sensors Offer a World of Always-On Possibilities, tinyML Use Cases and Applications. And today our speaker is Mahesh Chowdhary, Fellow Senior Director of MEMS Software Solutions from STMicroelectronics. Thank you to our tinyML strategic partners for committing to make tinyML to the next level together. AZIP, Analog Devices, Aeon Devices, ARM, DeepLight, Edge Impulse, EMSA, PhotoHub, Greenwaves Technologies, Gravity Inc., IBM, ImageMob, Itemis, Clickatech, Microsoft, Noda AI, NXP, OctoML, Prophecy, Keekso, Qualcomm, Reekson, Renesas, SAP, SensiML, Silicon Labs, Sony Semiconductor Solutions Corporation, ST, Stream Analyze, Synaptics, Sentient, and TDK Inventions. Join our growing tinyML communities on meetup.com and LinkedIn. You can see these links here, and they'll also be linked on the tinyml.org website. But we have over 12,000 members in meetup.com and 3,000 members in our LinkedIn community. So it's a thriving community, and we hope to see you there. Also subscribe to the tinyML YouTube channel. This is also where this talk will be posted after. And you can find out all the talks that we've done previously on youtube.com/tinyml. There's over 8.3 thousand subscribers, so we look forward to seeing you there. Our next tinyML Trailblazer series is coming up, our success stories with Luca Ver, live online on January 11th at 8 a.m. Register now by scanning the QR code on the screen. Our next tinyML talks are actually in person in Canada on Friday, December 16th with Andrew Kostick of Qualcomm and Asid Sabori of DeepLight. They'll be discussing an overview of the Snapdragon 8 Gen 2 Sensing Hub and also expanding possibilities for Edge AI with compressed and quantized CNN models. And this will also start at 7 a.m. Pacific time if you're not there in person. And please contact talks@tinyml.org if you're interested in presenting a talk like this one today. Today, our speaker is Mahesh Chowdhary. Mahesh is a Ph.D. and Fellow and Senior Director of MEMS Software Solutions at STMicroelectronics based in Santa Clara. He leads effort on development of solutions and reference designs for mobile phones, consumer electronic devices, automotive and industrial applications that utilize MEMS products, computing and connectivity products. His area of expertise includes AI and ML, MEMS sensors, IoT, digital transformation, and location technologies. He's been awarded 34 patents, and Mahesh has received the Ph.D. in Applied Science or Particle Accelerators from the College of William & Mary in Virginia. Mahesh, take it away, and thank you for joining us today.
Yes, good morning. Thank you, Jenny. So I'll be talking to you about how smart motion sensors offer a world of always-on possibilities, and I'll be discussing tinyML use cases and applications. So here is the agenda. So I'll start with a brief history and some market challenges. Then I'll talk about always-on high accuracy sensors. Next thing that I'll talk about is machine learning core that is built into the sensors that I'll be talking about. So machine learning core and finite state machines that are available inside these sensors can be utilized for a variety of these always-on applications. So I'll talk about those and use cases and finally some takeaways. So let's start with the brief history and the market challenges. So, you know, in early 2000s, that's where MEMS technology, came into being, and it started to get used in human-machine interfaces. So there were, applications such as gaming controllers that became very popular at that time. And then in the following decade, in 2010 and onwards, there was a very wide proliferation of these sensors in various devices, mobile phones to wearables. And now in this era, we did see a lot of these solutions that had cloud component to them as well. There was a lot of performance improvement in terms of sensors and fusion of technology. Then this was the online era. So now, from offline era to online era, now in 2020 onwards, we are in the era which we call as on life era. So in on life era, this is fusion of technology and life. What does that mean? Now, these intelligent devices, these sensors are able to not only sense, but also process this data on sensors themselves and take action. So with that, we can also see sensors, essentially in the initial implementation were, in a fragmented space where you had multiple sensors and devices. Then came the era where these sensors were connected, and sensor fusion became a reality. So, an example would be use of GPS and inertial sensors for automotive navigation system. And in mobile phones now, as you can imagine, there are 10 plus, 15 plus sensors that are available. Anywhere from touch sensor to microphone to inertial sensors and so on. And this now leads to the era where AI is not only at the edge, but it is now possible to have AI implementation in the sensors themselves. And why? The reason is the following: that we are when it comes to building devices and solutions, if you ask somebody who wants to build this device, they would have these five primary areas that they would like to see improvements. They would like to see more computing power and memory available for their solutions. They would like to see lower power consumption because many of these devices are battery operated. And for good user experience, you would like to have battery last a long time. You would have multiple sensors that are available for data collection, for sensing the world. Then, easy connectivity. So whether it is wired or wireless implementation, and more security, such that, these devices don't get hacked into. And lastly, faster time to market. So this is what the device creators, these are the challenges that device creators face. And let's see how we address them. So, one of the areas that we are going to be talking about today is always on high accuracy sensors that allow for many of these aspects that we talked about. Now, sensors are most commonly found in personal electronic devices that all of us commonly use. And there is a lot of innovation that has been occurring in the personal electronics space. So the very first thing that I wanted to, quickly, talk about is, what are, these personal electronic devices that most of us work with and deal with. So, they include smartphones, tablets and e-readers, wearable devices, personal care and hygiene products, gaming, drones, true wireless stereo headsets, and now augmented reality glasses. So, all of these devices utilize sensors in them for a wide variety of applications. So let's talk about wearables and accessories. And in case of wearables and accessories, there is provision of sensors, thanks to the processing capability and wireless connectivity in, these low power systems. The devices such as your fitness bands. These fitness bands have 6-axis IMUs in them for sports activity recognition. Your smartwatch would have a 6-axis IMU for gesture recognition and sports activity recognition. Your wireless speakers would have MEMS microphones for speech recognition. Hearable and true wireless stereo device headsets would have microphones and accelerometers in them for noise cancellation and user interaction, user interface. So now, if you take this to the next step and try and understand what are the challenges when we use sensors and AI on the edge, and why would you want to use them on the edge? So if you consider the scenario where cloud processing which was the paradigm, poses many limitations. Number one is latency. If the sensor data is sent across to the cloud where computations occur, and then actionable information is sent back to the device, this latency would make the user experience rather poor. There can be issues with network bandwidth and or connectivity losses. And that would again impact user experience. In many cases, data privacy is a concern where you would not want to have the data leave the device. For that reason, you essentially cannot have a cloud implementation. And lastly, there are battery operated devices where you would rather have an autonomous solution on them. And in those cases, you would want to have an AI implementation on the edge device. So when you consider sensors, how are sensors now changing in this past 10-year period? So, if you consider from 2010 to 2020, I have, some parameters here. So number one, we start with power consumption. So sensors, 6-axis IMUs in this case, used to consume about 6.1 milliamps of current, and it has come down to around 0.5 milliamp of current consumption. So that's about 91% reduction in power consumption. Noise reduction. So, sensor noise has come down about 73%. Where the power spectral density for a sensor now is, for an accelerometer, is now down to 60 microg's or square root of hertz. The thermal stability of gyroscope, it has, again, improved over by about 83%. So you can see it has come down to 0.005 degrees per second per degree C in terms of the thermal temperature stability for gyro. Gyro noise reduction, again, 87% reduction. So, the power spectral noise density for gyro is down to 4 millidegrees per second over square root of hertz in 2020, as compared to 30 millidegrees per second per square root of hertz in 2010. Same thing for size. It has come down about 70%. The dynamic range has increased about 100%. So instead of 2000 degrees per second, it has gone to 4000 degrees per second. In 2010, there were no features, the embedded features that were available in these sensors. And 2020, we had machine learning core, we had finite state machine, we had intelligent sensor processing unit, we have pedometer and sensor fusion. These are all available inside the sensor. And at the same time, cost has come down about 75%. So now let's talk about machine learning core in these sensors, which enables many of the aspects that I talked about for in-edge computing. So these sensors with machine learning core, have few main parameters that are so important. Number one is a reduced power consumption, both for the sensor as well as the system. If you can compute the needed data, needed information that is to be sent out to the user interface or whatever the ultimate use for that sensor may be, in the sensor itself, you are saving the communication bandwidth current consumption. So that immediately shows up as overall reduction in system power consumption. So now the machine learning implementation that we have in ST sensors, let's talk a little bit about that. So there are, two different approaches for machine learning. One is supervised, the other one is unsupervised learning. So under unsupervised learning, you have, dimension reduction, clustering, pattern searches. In case of supervised learning, you have, regression, you have, different methods of classification. So what we have available in the smart sensors that I'm talking about is ability to run decision trees on sensors themselves. So these sensors are, 6-axis IMUs, accelerometers and gyroscopes, and you have 3-axis accelerometers that have machine learning core in them. You have inclinometers that have machine learning core in them. And the concept of decision tree is that, it's made up of these different, nodes. Each of these nodes essentially would have an input condition, and it would have a true path and a false path. So essentially you traverse down the decision tree to ultimately reach a decision which could be, classification. Now, this particular approach is somewhat different from a standard approach, when you are trying to solve a particular problem. So in a standard approach, when you are trying to solve a problem utilizing sensors, you would develop a model of the problem that you're trying to solve, whether it is classification problem or any other such problem. In case of machine learning approach, you would collect lots of data, label this data, and develop a machine learning model that is implemented and which solves this particular problem. So the approach that you would take in programming a sensor with machine learning core would essentially follow the same pattern. The very first thing that would be done would be to define the classes, which you would want to have the classification engine detect for you. Examples could be, if you pick an example of human activity recognition, you can indicate classes to be stationary, walking, running, jogging, so on and so forth. So you'd capture data for all of these different classes. You would label this data, and then you can use any of the available software tools to build these decision trees. Next step would be, once the decision tree has been tested and verified that it performs well, you would embed this decision tree into the sensor and finally run the machine learning model in the sensor. The tools that are made available from ST for this approach, I'm listing some of them here. So you could have sensor data available for accelerometer, gyroscope. You can also connect an external sensor to a 6-axis IMU that has machine learning core in it. The external sensor could be something like a magnetometer or a pressure sensor that is brought in, and that data could be utilized in machine learning core as well. You could use tools such as Unicleo. You could use ST BLE sensor app, or Unico GUI or Algo Builder. Now, for the process of labeling data, building decision tree, embedding the decision tree, and then processing this, again, in the various tools that could be utilized. So tools such as Unico can be used to, capture data, label data, and also build decision trees. And these decision trees then can be embedded through a UCF file that is generated, which contains the decision tree. A variety of external tools could also be utilized, and these tools could be, Weka or MATLAB, Python, or RapidMiner. Any of these tools could be used to create a decision tree from the data that has been collected. Moving on to the process, so you could use a variety of boards that are available from ST, such as professional MEMS board, which is available, where you would connect this board to your PC through a USB cable, and you would run Unico GUI on laptop. Or you could use SensorTile.box with STBLE sensor app, and which essentially will allow you to capture data. Or the third option could be that you could use a Nucleo board to collect data. Once the data collection is done, labeling is the next aspect, where you can apply labels to data. So in case of an example for human activity recognition, for each of the logs that you have collected for stationary, walking, running, jogging, driving, biking, all of those would be appropriately labeled. And you would ultimately create an ARFF file, which is, attribute relation file format. ARFF stands for that. You'll create that file. You'd specify, the sample rate, full scale range, the window length, all the filters that you want to apply to the sensor data, all the features that you want to use for the decision tree generation. All of that is done. And finally, you create an ARFF file. So this ARFF file now is ready to be processed by any of the tools, such as either Weka, you could use Python, you could use MATLAB, RapidMiner, or you could use the tool built into Unico, which can generate the decision tree for you. So this decision tree, can be in form of a text file, and this text file, can be embedded into a header file that you would utilize where this decision tree is downloaded into the sensor using the I2C or the SPI or the I3C interface to the sensor. And once this is done, the output from the sensor could be visualized using any of these tools such as Uniqlo GUI or Unico GUI or Algo Builder, which allows you to not only build the decision tree but also use any of the other software libraries along with it on in a PC environment, or you could use STBLE sensor app. So a very wide variety of examples of machine learning core solutions are available on GitHub, at this specific location. So I'll talk about some of them. So let's talk about some of the features for machine learning core. The very first thing we wanted to do was to talk about differences between what can a machine learning core do and what can a finite state machine do. So machine learning core can run a decision tree, which can do classification, and it would identify a pattern which will match to one of the classes that you have designed the decision tree for. In case of finite state machine, it can be used for features such as gesture recognition, where the sensor data could be compared against certain events or thresholds that are set up or timers that are set up, and the output from a finite state machine would be some event detection based on the certain conditions and thresholds that are met. In case of machine learning, machine learning core, the output would be the pattern classification from the decision tree. So, some examples of what, in case of a personal electronic device, what you could have decision tree do. It could, do activity recognition for mobile devices or for wrist-worn devices. It could do sleep monitoring, hand wash detection, head motion detection, vibration monitoring, gym activity recognition, yoga pose, position determination. All of these classifications could be done for a personal electronic device using a sensor with machine learning code in it. And many of these examples are available on our GitHub. In case of finite state machine, it can be used for a personal electronic device to, in case of a fitness band or a smartwatch, it could be used to detect wrist tilt, to light up the display when the wrist is tilted. It could be used to detect free fall, flip up or flip down. It could be used to detect wake up or glance or shake or pick up or 4D case, which way is the device oriented. All of these could be done using a finite state machine. So a combination of finite state machine and machine learning core essentially will make a very wide variety of applications possible. So some of them I'm listing here along with the current consumption, which is the most important aspect of this approach. So a gym activity recognition classification could be done by machine learning core, where the sensor current consumption would be about 10 microamps, and the logic running in machine learning core and finite state machine will consume about 7 microamps. So for a total of 17.5 microamps, gym activity recognition could be run inside the sensor. Similarly, wrist tilt. So as you can imagine, you would want to run this scenario of wrist tilt all the time. And this wrist tilt implementation, running in the sensor would about consume 10 microamps for the sensor current consumption, 6 microamps for the machine learning core finite state machine implementation, which is the computational part. So for a total of 16.5 microamps, you would have the ability to run the wrist tilt logic using accelerometer plus machine learning core all the time. So this is, as you can imagine, orders of magnitude less current consumption than when this logic is running on an application processor. So something similar for sleep monitoring. So 12 microamps of current consumption, and you can run sleep monitoring logic on the machine learning core all the time, where the computational part of it is 2 microamps of current consumption. So let me talk, about which sensors do this. So there are a wide variety of sensors that can, essentially do this. So LSM60SOX, LSM60SO32X, or these are targeted more for devices which would be utilized for activity recognition, for airplane mode detection, those kind of scenarios, and devices that use an application where thermal stability is more important, sensor noise is a lot more important. So then there are applications, there are sensors such as LSM6DSRX, which could be utilized for that. So virtual reality or, sensor fusion kind of applications can use this. The latest sensor which we have, LSM6DSV16X, is a best of both worlds. So it's the lowest power consumption and best thermal stability and the lowest noise, which has machine learning core and finite state machine available in it, which will allow you to run all of this logic in the sensor and still achieve that great power efficiency, which we talked about. So I'll talk about some of the applications now. So gym activity recognition. So this is an application that is available for LSM6DSV16X. It will identify, the machine learning core in this case will identify 4 scenarios. And those 4 scenarios can be, no activity, or detecting bicep curls or lateral raises or squats. So machine learning core logic will, do all of this processing. So there is no pre-processing required from MCU. And, in this particular case, you could use any platform that I talked about. So it could be your Profi-MEMS board or your sensor tile with LSM60SV16X, or a Nucleo board with LSM, with LSM60SVX available on it. And in our case, what we had done is we acquired the training data using sensortile.box. And sensortile.box, is a device which is easily possible to strap it on your wrist and collect data, easy to carry. So that's why we utilize this. But you can test it using any of the available platforms. Most important point on this thing is that the current consumption for this is about 7 microamps. Another example is yoga pose determination. So this can detect 13 different classes for 13 different kinds of poses using machine learning core. So all of this logic runs inside the sensor. Again, in this particular case, you can use either a Profi-MEMS board or a sensortile.box. The result output would be one of those classes that is detected when the user is using this device to do yoga. And the decision tree in this case was generated using Unico, the tool built inside Unico to take your ARFF file and then generate the decision tree. And we are using in this case LSM60SV16X as the sensor, which has both a 3-axis accelerometer and 3-axis gyroscope. So it consumes 9 microamps of current to do the computations for yoga pose detection. Another one is head gesture recognition. So head gesture recognition can be useful for either a headphone or AR glasses. So machine learning core will identify any of these 5 scenarios, such as nod or shake, stationary, swing left or swing right, walking. All of these scenarios can be detected by the sensor in your glasses or your headsets. So LSM60SV16X can essentially do this. In our case, we acquired the test data using sensortile.box, and this particular solution is, of course, available on GitHub, where you can download this and use this to try the solution out. Current consumption for this 9 microamps. So for an always-on, highly accurate classification, 9 microamps of current consumption is something that is again paradigm changing. It's very small current consumption for devices that have very small batteries, such as AR glasses. Human activity recognition. So 5 scenarios, 5 classes here. Standing, walking, running, bicycling, or driving. And these can all be detected in the machine learning core, where the logic is running on the MEMS ASIC. Again, no pre-processing required from the MCU side. You could use any board, but in case of a sensor tile.box, the advantage would be that it's a device that can be easily strapped on your wrist or very easily carried if you want to conduct testing or data collection. So 4.5 microamps of current consumption. So for activity recognition logic that's running on your device all the time, this is orders of magnitude smaller amount of current consumption as compared to this logic running on a microcontroller. The other example that I want to share here is that you can have a combination of both. You could have some logic running on the microcontroller and the sensor running, another set of logic. So you could have a audio scene classification. That logic could run on microcontroller, and sensor could run human activity recognition. So if you can imagine this, that if the device is stationary, if there is no change in the environment, there would be no reason to constantly do your audio scene classification, because if you're running this logic on the microcontroller as well as you have your microphone powered on, the current consumption for this scenario is rather high. So if the sensor can do the primary detection, whether it could determine if you are in a car when you're driving, or if you are walking, if you are riding a bicycle, you can do the audio scene classification based on if you have moved from your original position. Let's say you have been walking in a mall, in the microphone essentially can pick up the audio and do the audio scene classification and make a determination that you are in a mall, or you are in an office space, or you are on a beach. So the process for this, you can imagine, would be collection of, same process, you would collect data and label data. So recordings of audio data are made using that a device. Maybe you can use sensor tile.box for that. It has a microphone in this as well. So all your pre-processing and preparation for neural network training and testing can be done after that. Your neural network topology definition, training and testing can be done using any of your deep learning frameworks that you prefer. Once that is done, then your optimized neural network code can be generated, can be processed and further generated for implementation on an STM32 using STM32cube.ai. And then this particular code can be uploaded onto the STM32 MCU. The sensor inside the sensor tile.box, LSM60SOX, can run the human activity recognition logic. So the human activity recognition logic can trigger to turn on the logic to be run on the microcontroller for the audio scene classification. So it's a combination of the two, and thereby you achieve greater power efficiency by combining two such approaches. Another example in this case, LSM60SOX sensor is used in a smart kettle, where the machine learning core will identify, three different classes here. Either the idle state, or when the heating up state for the kettle is occurred, or when the water in the kettle is boiling. And this can be done using the LSM60SOX sensor, which has a 3-axis accelerometer and gyroscope. The results are output using STBLE app, and the training data was also acquired using STBLE app in this case. So this is also available on GitHub. Then a series of applications here which pertain to laptops and PC kind of devices. So LSM60SV 16X sensor, which has machine learning core and finite state machine, can be used to do in-bag detection. So when the laptop is in the bag, if it is detected, then we can prevent scenarios such as laptop overheating and extend the battery life and improve the user experience. So in this particular case, there are 3 classes that can be detected for the in-bag carry condition. When the user is stationary or walking or running, or is in a transportation mode of in a vehicle mode, and it will essentially detect the in-bag condition with these 3 classes detected inside the machine learning core. Then you can also have a finite state machine embedded inside LSM60SV 16X, detect out of the bag event. And it can be used to automatically wake up the laptop when it is taken out from the bag and positioned on a flat surface. So the current consumption for this is about 7 microamps. So you can see here in this scenario that to run this logic all the time with such tiny amount of current, this useful feature will improve the user experience quite a lot. The other algorithm that can benefit from machine learning core is on-table detection. So machine learning core can identify 2 scenarios to determine if the laptop is on the table or not on the desk, not on the table. So how can this be used? It can be used to adjust the laptop thermal profile policies. So when the laptop is detected to be on the lap, the CPU essentially can be adjusted to not to generate as much heat and injure someone. And this logic runs inside LSM60SV16X and would consume only 14 microamps of current. Another scenario is to detect pickup for laptop. So the finite state machine embedded inside LSM60SV16X can be programmed to detect pickup event, and it will support all of these different scenarios like clamshell mode for the laptop, tent mode, stand up, lid closed, or the tablet mode, all of these scenarios. And this logic would consume 5 microamps of current consumption. Another one is lift up detection. So it can be used to automatically turn on or off the screen when the device is lifted up or lifted down. And this is only based on accelerometer data. So the MLC embedded inside the LSM60SV16X sensor is programmed to filter the accelerometer data, and then finite state machine inside the sensor would detect lift up or lift down. Current consumption for this is about 5 microamps. The other use case scenario here is again for laptops, a scenario where you can do activity recognition and carry position determination. So is the laptop being carried in lateral scenario, or laptop is carried in front, like you're holding your laptop and walking with it, or is laptop in your backpack? And is the user walking, running, or stationary? So all of these scenarios can be detected using machine learning core inside LSM60SV16X with about 10 microamps of current consumption. Here is another useful feature that LSM60SV16X has, which is to utilize a finite state machine and QR to detect single touch, double touch, triple touch, long touch, swipe left or up, swipe right or down. All of these could be done using electrodes that you have here, the output from these electrodes is processed in LSM60SVX and finite state machine built inside it. For touch, the current consumption is 82 microamps, and for swipe about 47 microamps. Now let's talk about some of the automotive use cases using MLC and FSM. So for automotive use cases, there is a sensor which ST has, which is called as ASM330LHHX. This is an automotive grade IMU supporting AI, and is utilized in a wide variety of applications such as dead reckoning, V2X, telematics, e-tolling, anti-theft systems, impact detection and crash reconstruction systems, motion activated functions, vibration monitoring, and this particular device has a size of 2.5 by 3 by 0.83 millimeters. It's AEC Q100 qualified, and it's in mass production. It has an embedded machine learning core and finite state machine. So some of the applications for this are, this is a car care application. When your car is parked, and you could have a scenario where somebody bumps into the car, whether it's a pedestrian or a bike or some object hits the car, a shopping cart hits the car. So this logic can be run while the car is turned off and sensor is powered up. So for a current consumption of 2.3 microamps, where you're sampling the accelerometer at 12.5 hertz, you can detect this. So this logic is running inside the sensor, and we'll be able to log the event. If needed, it can generate an alarm, and thereby wake up the main TCU, and the alarm could be raised. So this is powered by the logic built inside ASM330 LHHX, where you could run the logic inside FSM and MLC inside the sensor. Another application for automotive use case is to detect is the vehicle being towed away, or is somebody jacking up the vehicle to steal the wheels when the car is parked. So as you can imagine, the engine is powered off. So you would want to have minimal current consumption. Otherwise, if the car is parked for weeks, the battery of this car could be drained. So here you can imagine we can detect three different types of events. If front or the back wheels are lifted, or if forward or backward lift using a flatbed, tow truck has been done, or tire jack detection, can be done. So in this case, again, accelerometer is sampled at 12.5 hertz, and the current consumption for running this logic inside the sensor is about 3.6 microamps. So how does this work? So in the case of both of these kind of jack and tow detection, you have two different kinds of threshold for each of the sensing axes, both for the positive sense and the negative sense. And if these if the sensor value exceeds the set thresholds, it would essentially detect the event. You can control the sensitivity of this solution by adjusting these values, and the user can set them up, or the car manufacturer that is utilizing the solution, or an aftermarket company that's utilizing the solution, can adjust this for a class of vehicles. So here you can detect a towing or jacking up of the vehicle. So it can detect scenarios such as, is the car stationary? Is the car being lifted up? Has somebody bumped into the car? Is the car moving? All of this could be done in single-digit microamps of current consumption. So what does the sensor data look like? In case of stationary data, you can see the three axes of accelerometer data, essentially here in this plot. When the vehicle is being jacked up, here you can see the variation that is observed in the orange trace here. You can see slight drift, and this can be detected by the logic running inside the sensor. When the car is moving, of course, you will see larger noise as compared to the stationary. When there is a bump or a crash, something bumped into the car, you would see events that are shown here in this kind of in this plot. So this is actual data from a vehicle. So I'm showing you here this to give an appreciation of what each of these events and what each of these scenarios looks like. So stationary, driving, jack up, crash, all of these, if you utilize accelerometer only, then in this case the current consumption for machine learning core is about 11 microamps. If you just want to do vehicle stationary detection, current consumption is about 6 microamps. If you want to detect towing, current consumption is about 3 microamps. So for approximately about 10 microamps of current consumption, such automotive use cases are now possible, where you can detect driving, jacking up of the vehicle, towing away of the vehicle, some car care applications, like somebody bumped into the car, or there was a stationary crash into the car. And these solutions are available on GitHub, where you can download this solution and try them out. So now let's talk about some of the takeaways from this discussion. So we have a wide variety of tools and resources available to try out some of these machine learning solutions in the sensors. So there are these function packs that are available for quick prototyping. So these function packs, they contain everything from a low-level device driver to middleware to a complete application, which you could run on a microcontroller and sensor connected to it to try out, such an implementation. So then there are these development kits that are available and GUI tools that are available. So development kits such as SensorTag.box or Nucleo board or STWin board, and GUI kits such as Unico or Unicleo that are all available. GitHub has, a very wide variety of such use cases and applications for such use cases that are available. They can be downloaded and tried. There are some sample data sets that have been also made available on GitHub, which can be used to try out the whole tool or Unico tool for generating a decision tree. A bunch of videos and training material is available. So these videos, show the step-by-step process for collecting data, labeling data, generating a decision tree, downloading the decision tree, and looking at the output while you're trying to build your solution. And of course, there is a community, a MEMS and sensor community where users can post their questions and receive feedback from other community members on this. So some of the takeaways, provision of these sensors in a very wide variety of use cases will continue to grow, as we have seen. Starting with simple use cases. And gaming controllers to now, running logic inside these sensors. We have come a long way, and it'll continue to grow. So multiple sensors, intertwined nodes, and edge processing and more is going to continue to happen. Now, as I indicated, this on-life era, here it essentially is going to call for local fast processing and intelligent sensor processing of data. So the logic inside the sensor would be, processing a fundamental sensor data information and only transfer metadata as needed to the gateway or to the cloud. And for the gateway logic to take appropriate action using this information would be the trend that we would see. A variety of use cases that we have looked at in consumer and industrial and automotive space. And for all of these, the most important point to convey here is that machine learning core and the finite state machine inside these sensors enable running many of these always-on scenarios where the current consumption is in single-digit or double-digit microamps of current consumption. And that brings me to the end of the presentation. Here's my contact information, and I can now answer any questions that we may have here.
Great. Thank you so much for that great presentation. And we have a bunch of questions in the Q&A that we can go through. And I'm just going to request remote control again. Okay, great. And everyone, please go ahead and take the poll that should pop up on your screen. But okay, we have a few questions here. The first one is, why was decision tree supervised learning considered in ST smart sensors?
Decision tree as logic, utilizes the most easy to understand and intuitive way of doing classification. And it's easy to implement, it's easy to understand, easy to design. And to build algorithms, generally you would use features such as mean or variance, energy in the band, peak-to-peak value, zero crossing, all of those features. And those can be embedded inside the sensor easily. And a decision tree essentially can use these features and do classification. So that is one of the quick answers to why we chose to do decision trees.
Great. And are there file systems that are used in storing data, and the models have unique features that make them suitable for IoT systems?
So sensor itself does not have a capability of running, a file system in it. You would only execute a decision tree or a set of decision trees inside the sensor. You can run up to 8 decision trees inside the sensor. You can run up to 16 finite state machines inside the sensor. And the output from this would be, either an interrupt or, it would be a status register, which is, read by microcontroller that is monitoring the sensor. So to store the data, label the data, you would utilize microcontroller or any of the other gateway logic to do that.
Great. And how much flexibility is provided by ST tools for discussed use cases to end user to modify or add labels, add or update ML algorithms that are most suitable for the chosen application?
Oh, yes. Tools such as Unico will give you a great degree of flexibility in how you can apply labels. Scripts are available from ST, which will allow you to, process very large volumes of data that you have collected and labeled. And you can process them. You do not have to utilize the decision tree generation tool inside ST's tools. You could use any of the tools that you may use right now, like MATLAB or Python or RapidMiner or any of the favorite tools that you may have. Decision tree generated by these tools can be then downloaded inside the sensor using the approach that I had described earlier. So there is a great deal of flexibility that is possible, and we provide scripts which allow you to process very large volumes of data, and you can utilize your own repositories of data and process all of this on your own machines to achieve the design part of this whole process.
Great. The first sub $50 navigation grade capable multi-axis MEMS internal sensors and inertial sensors will become available on the market for the first time next year. What applications do you feel will be most in need of such a drastic increase in accuracy versus consumer grade devices that will now be available at such a low cost?
I missed part of the first part of the sentence, the question. So would you kindly repeat, Jenny?
Yeah, so they're saying that the first below $50 navigation grade capable multi-axis MEMS inertial sensors will be available on the market next year. And what applications do you feel will be most suitable for those devices that are now at such a low cost?
Oh yeah, so there is quite a lot that is possible using such devices. So as I was discussing during the automotive portion, automotive use cases portion, if these sensors can detect whether the vehicle is stationary or vehicle is turning at a certain rate, the vehicle is driving in a straight line, if these such applications will these ability to run and logic to detect all of these conditions will improve the overall performance of a automotive navigation system. So this logic can be run inside the sensor for microamps of current consumption, and thereby you can divide the computation between different blocks. You do not have to use a very complex logic. If all you need to do is to determine whether the vehicle is moving or stationary. So when the vehicle is moving, that's when you can start to apply, a lot more complex logic, and thereby, have a highly accurate navigation system algorithm generate the position. So that's how, we can see, dividing off the computation. A computational chunk running inside the sensor does one piece, and other logic running on a microcontroller that would do another part of the algorithm, more complex part of the algorithm, and achieve improved user experience and accuracy.
Great. And how is the current consumption of the events estimated? I think you had a slide where you had current consumption estimates listed, and they're wondering how that was measured.
Yes, so you can measure the current consumption, at the sensor itself. And we have tools available which will allow you to do that. Using any of the ST tools like professional MEMS board, you can actually make the current consumption measurements to measure what is the sensor current consumption and what is the machine learning core and finite state machine logic when it's running inside the sensor. What's the current consumption for that?
And are there any innovations in geolocation sensors or other such operations? They also mentioned a great use case would be theft tracking. Do you have any insights on that?
Absolutely, yeah. So, the towing, jacking, and bump detection essentially give you an example of what is possible. So
Mm,
for sure, many of these other use cases are, quite possible with logic running inside the sensor. Key thing to note here is that you cannot consume too much of current because let's say the car is parked at a parking garage for several weeks. When the user returns to the car, they would want to turn it. They would want to see a battery that is not drained and still be able to turn on the car and drive away. So that's why if logic running inside theft detection kind of logic that's running inside the sensor, which consumes maybe single digit of microamp of current consumption, it will do the important aspect of theft detection, and at the same time it will not drain the battery.
mm.
So, which is why this use case makes all the sense to utilize MLC and FSM running inside the sensor to be able to do it.
Very interesting. And finally, our last question, beyond just data collection and synthesis by devices, are there possibilities of improved energy efficiency of devices that is driven by ML?
Certainly, there can be use cases where in a simple fact, if you can detect that the device that you are, I use the example of this kettle. The kettle, you can have a kettle is idle, kettle is boiling, and kettle now is heating up. These three states can be detected by sensor and the logic running inside the sensor. So this is an example of how you essentially, through this kind of contextual awareness, reduced overall current consumption. So what I would say here is that these sensors enable contextual awareness, and contextual awareness applications and logic that can utilize such chunks of logic running on the sensor itself at very low current consumption will improve the overall system efficiency and thereby help achieve such power reduction.
And looks like we just had a couple more questions pop in that should be quick, but one of them is, do you have any advice for someone who is just starting out in their tinyML journey? Or resources related to it?
So I had listed some of the resources. Maybe I can go back to this slide here. Yeah. So we have a variety of such resources that are available. So these function packs essentially will give you everything. You do not even need to write a device driver for sensors. It has everything in it. It has device drivers, it has middleware, and has a complete application that's available. So these are available from st.com to work with the sensors from ST. We have these hardware kits that are available, sensortile.box or Nucleo platform or STWin. These are available. There are many examples that we have on GitHub, and easy to understand step-by-step videos that we have posted that can be utilized. And there are similar resources that are available on the web, which a user can take a quick look. And last but not least, there is a community forum that we have here where people ask questions for anything that they're stuck on, and we provide responses. And forum members also, I have seen, provide responses to commonly asked questions here. So all of these resources can be utilized by somebody who's just starting out.
Great. And then just a final quick question before we go to the outro, but does ST also offer these sensors with open synthesis packs in the ARM ecosystem?
Yes, ST is an ARM partner, and yes, indeed.
Great. Thank you so much for this really interesting talk today. And thank you everyone for asking such great Q&A questions. We'd like to thank our tinyML strategic partners for committing to make tinyML to the next level together. And we'd like to thank especially our executive strategic partners, Edge Impulse, the leading development platform for EdgeML, Qualcomm, advancing AI research to make efficient AI ubiquitous, accelerate your edge compute with Sentient, making edge AI a reality, Platinum strategic partners, DeepLight, the fastest video analytics solutions on ARM CPUs. Clicatech, global IoT solutions. Renesas, enabling the next generation of AI-powered solutions that will revolutionize every industry sector. Sony Semiconductor Solutions Corporation, and our gold strategic partners. Analog Devices, ARM AI, PhotoHub, Microsoft, NXP, STMicroelectronics, ST, Synaptics, and our silver strategic partners. We have, just a reminder, we have our next tinyML talks in person in Canada, and we'll also have a webcast at 7 a.m. Pacific time on Friday, December 16th. And please email us at talks@tinyml.org if you're interested in presenting. Thank you everybody for joining, and hope you have a great rest of your day. And thank you, Mahesh, for the great talk.